I would like to introduce our speaker, Kian. His topic is optically pumped magnetometers, and he is going to be walking us through the brain imaging that's associated with them. Let me just open this up for your bio. So Kian is a physicist with a degree from UNC Berkeley, where he graduated in 2021. During his undergraduate years, he gained valuable experience as a research assistant in nuclear engineering and graphene-based nano devices. He furthered his studies by pursuing a master's degree at Imperial College of London, contributing as a graduate researcher at the Quantum Science and Device Facility. Currently, Kian is completing his PhD at University College of London, focusing on the applications of quantum technologies throughout his academic journey. He has amassed significant experience working with various quantum startups and national laboratories, solidifying his experience in the field. Thank you so much, Kian. I am going to allow you to share your screen and let me know if you're able to do that.
Thank you very much. So first off, thank you very much for inviting me. Juan Carlos reached out and we were in the Qubit by Qubit program. So thanks again for the opportunity to speak. Today, I'm not going to be talking about quantum computing per se, but this is a quantum-inspired technology called optically pumped magnetometry. And we're using this at the moment for a lot of different applications, but the one I'll focus on for today's talk is primarily going to be for brain imaging or neuroimaging. So just before I start, a bit of background about myself. Nydia already mentioned, so I'm a current PhD student at UCL, and I'm also a teaching assistant for the Qubit by Qubit program. I just wanted to advertise and say if you're interested about quantum computing, it's a great program, offers a lot of support, and teaches you a lot about quantum algorithms. So take a look at their website. I did my master's and a lot of projects on quantum hardware. So like you already mentioned, fabrication of some devices, characterizing some quantum circuits, and now some laser stuff. But again, what I'm going to talk about today is not quantum computing. It's actually, again, it's another quantum-inspired technology. And just to show you that beyond quantum computing, there are a lot of things that we're trying to achieve with quantum in general. So in terms of the content, I'll start off with a brief introduction to squids. I'll follow this up with how squids are used for brain imaging, or also magnetoencephalography. And then I'll talk about these optically pumped magnetometers, OPMs for short, for the purpose of brain imaging. And then I'll just follow this up with some ongoing challenges that exist and an outlook as to what's going on. So if at any point you have questions, do feel free to drop into the chat and I'm happy to answer them. So first off, superconducting circuits are big in the world of quantum, and the big players are using these circuits a lot. These include Google, Rigetti, IBM, and all of them have created different numbers of qubits, but it has a lot of advantages over other qubit architectures. Some of these are included over here, so they have a lot of high fidelity operations, which means they're incredibly fast. They have relatively long coherence times. And most importantly, we have a lot of experience in electrical engineering that help us engineer and tune these qubits precisely. So it's one of the leading architectures for qubits at the moment, superconducting qubits. And it goes back to the principles of superconductivity. And for that, we have to remind ourselves why superconductivity is good in the first place. It's actually allowing us to control a lot of quantum effects that come up. The good thing is that we are also taking a lot of experience and expertise from the semiconductor industry, and we're transferring it directly to the development of superconducting quantum chips. Another good thing is that it has minimal dissipation, which means we're trying to create a closed quantum system and apply specific gates to those closed quantum circuits that we're using as qubits. At the heart of these superconducting qubits is actually something called a squid. Now, the squid itself stands for superconducting quantum interference device, and this is what it looks like. Basically, to the left is the circuit structure of what a squid looks like, and you could see it's basically a loop. And within this loop, you have two junctions where the blue are superconductors, and the orange in the middle is an insulator. So if I take one of these superconductor sandwiches and I open this up over here, this is what I'm looking at. So it's an insulator sandwiched between two superconductors. And this is called the Josephson junctions. And if you put two of these in parallel, you get a squid. Now, the squid has a lot of different applications, but mainly it's great because it's a nonlinear element. And if you've heard of inductors before in classical electronics, this is basically a non-linear inductor. And it has, as I mentioned, a lot of benefits. The way we're using it for qubits is the fact that it's allowing us to create distinct energy spacings that let us isolate a two-level system among a lot of different energy states. So this non-linear inductor means that we have non-linear energy spacing. So we can take away the ground state and the excited state and isolate this from all the other energy state. That means we have a well-defined quantum two-level system that we can use as a qubit. Now, just last slide on qubits and squids. We took these squids that existed from a long time ago. We incorporate them into superconducting circuits that are a bit more complicated, and we created better and better versions of qubits, basically. So this is the modern transmon qubit that you see a lot of different superconducting companies use, and this is what it basically looks like. It's a cross, and at the very bottom of this cross, you see that's the squid. Remember, that's the loop that I talked about in the last slide. That's how the squid is being used as a qubit. And you see this type of architecture used by different groups like Google, and that's the Google chip over here, one of their very first chips that demonstrates what a qubit looks like in this context. So at this point, I think we're all familiar, we've heard of superconducting qubits, but now I'm going to talk about another application of squids, which is the application of squids for magnetoencephalography. And what that basically means, magnetoencephalography, is basically measuring the magnetic fields created within the brain caused by the neuronal activity. So if you have a neuron moving from one point to another point, this is generating a current. And as we know, a generated current is also going to induce a magnetic field, and detecting that magnetic field is going to allow us to understand which part of the brain is doing a certain activity or task. So this is what a squid MEG system looks like. Basically, the participant goes and sits inside. The reason why you have this huge setup on top of the participant is because we need everything to be cooled to superconducting temperatures. So all of this is basically a very cold refrigerator, similar to what we see in quantum computing as well. All of this is cooling things down to almost 2 Kelvin temperatures. So as you can see, the participant is very limited in the movement that they could be having. They're just stuck inside this huge chamber, and they can't really move their head a lot, which means the experiments that we could do for brain imaging are very restricted. We can't do realistic experiments too much because for realistic situations and environments, the participant would actually be moving around and looking. But in this case, all we could do is just present pictures to the participant, or maybe just have them wear a VR headset. But at the end of the day, this is the type of data that's being collected from MEG systems. It's basically projecting all the signals that it's collected onto a brain, and it's telling you, okay, this is where that signal is coming from. So for instance, in that particular experiment, maybe it lights up this certain part of the brain, and then neuroscientists can go and say, okay, this part of the brain is associated with these tasks. So this is what brain imaging is doing, and this is how we've done them with squids. Now, the exciting part is that these huge squid MEGs are might be replaced by a much more compact and wearable alternative called the optically pumped magnetometer MEG. And as you can see, this OPM MEG is a lot easier to use. It's just a cap that you put on. You have a backpack that all the control electronics are connected to, but it doesn't require cryogenic cooling anymore, which means you can get rid of this huge system that you had for squid MEGs. Now everything is done at room temperature. There's only a bit of heating going on in these sensors, but apart from that, everything is done at room temperature, and you could actually have these sensors on your head, and you could move around with it to some degree. So that's the alternative that OPMs are providing. They're wearable alternatives, but they still give you very high spatial and temporal resolution, enough for us to be getting very distinct and clear brain signals from the participants. And we could use that for a variety of different experiments. A lot of that right now is focused on spatial navigation. So we put these headsets on participants, we ask them to move around, and based on the brain's response to their movements, we're getting some very important information about how their brain is working, and it's helping us unlock and solve a lot of questions we had about the brain, basically. So these are the type of questions and tasks we want to be doing with these new sets of OPMs. And that's just an example of what acquired OPM data would look like. As I mentioned, these are magnetometers, which means they're measuring the magnetic fields that are coming out. And all these different colors that you're seeing, each of these colors corresponds to one of these sensors. So you have a lot of different sensors measuring a lot of different magnetic fields. And at particular time points, you're getting spikes in those magnetic fields, which means, okay, the participant's brain is having some reaction to something that they're seeing. Now, the reason why this is a quantum-inspired technology goes back to the fact that in these sensors, you have individual atoms that we're using for sensing. The main atom for the sensors in this lab are based on rubidium atoms, and these are alkali atoms, which means they have an outermost electron that we're manipulating. But basically, in this little box over here, you have a lot of these rubidium atoms, and you're shooting a laser through this vapor cell. And depending on how much light is coming out, that's determining which state your atoms are in. So the reason, again, that it becomes quantum, it's actually atomic as well, is because we're leveraging or we're utilizing the fine structure and the hyperfine structure of these alkali atoms. And depending on the energy states that they're ending up in, depending on the degenerate energy states, we can tell whether this particular sensor measured a magnetic field or not. And we can also tell how much of a magnetic field it's measured. So that's effectively how we're using these sensors. If you break one of them down, this is what it looks like. This is one single sensor. It's the size of a Lego brick. Inside this Lego brick, you have this setup over here that has a laser, a vapor cell, and a photodiode that's measuring how much laser is coming out. Now, in terms of the data that we're seeing, like I mentioned, this was the setup. The laser, what's happening over here is that it's pumping all of these alkali atoms up into an excited energy state. So this is the physics principle behind it. Once all of these atoms are up, the laser light is not going to be absorbed by any of the atoms anymore because they're all already at the excited state. So it's just going to go straight through to the photodiode, which means when all the atoms are optically pumped or excited, all the laser light is going to go through. Now, what happens is that a transverse magnetic field applied to this sensor is going to knock out these atoms out of the excited state, which means the laser will need to re-excite the atom. So it has to pump the vapor back into the excited state. And this is what that output would look like. So as I mentioned, if there is a magnetic field being picked up, it's going to knock off the atoms out of the excited state. And that means laser is going to be absorbed. So not all the laser is going to go through. But if all the atoms are in the excited state, it's going to get absorbed. It's not going to get absorbed anymore. So now this is the type of output plot that we're seeing from the data. It's basically a voltage over applied field plot. And at this moment where there's no applied field, so if there's no external magnetic field, all the laser is going through. So we have the highest output being measured there. But as soon as there's a magnetic field applied, it's going to the laser light is now going to be absorbed by those atoms, and that's where we end up with these other values along this Lorentzian curve, basically. So that's effectively the mechanism that allows us to detect magnetic fields in the first place using these sensors. Now, for the sensors that I've been using, these are the type of data results that we're looking at. So over a long range of time, I'm measuring how much the measured magnetic fields are across all the different channels on these headsets that I showed. So on these headsets, we have almost, depending on the experiment, but we have almost 100, even more of these Lego bricks attached, and each of these is measuring a magnetic field, and that's what each of these colors are representing over here. Yeah, in terms of the raw output data, we started off with that cap. I showed you the type of results that we should be getting from those caps. And effectively, all they're doing is measuring a magnetic field over. And there's a lot of post-processing that's involved with this. But in the end, you should be ending up with data or information that looks like the one I showed before. This is called the source localization process, which means we went from raw data from these sensors and we did a lot of post-processing, different types of techniques, and we managed to localize the signal to one particular part of the brain. And that lets the neuroscientists understand, depending on the experiments that they're doing, how it's impacting the participant and their brain and which part of the brain is being activated based on that experiment. So now I'll just quickly mention the experiments that I've been using, or at least the data that I've been using. It's been collected by another researcher in the same institute, giving credit to her over here. So her experiment actually focused on 8 participants. And what was asked to do was for each of these participants, they were asked to close their eyes and they were asked to imagine moving forward like this. Imagine moving backward, imagine moving rightward, leftward, backward, forward, leftward, and rightward. So these participants, they're not physically moving, they're just imagining moving forward and backward. And the cool results that we got from this was that based on the signals that have been detected, we could tell what the participant or which part of the brain is being activated when the participant is imagining moving forward. And we could distinguish that from the participant imagining moving leftward or backward. So I think this was a very cool result that showed that with these sensors, we have the sensitivity to kind of decode imaginative movement to some extent. And that just means the better these sensors get, the more we can unlock and understand about what's going on inside the brain. So a huge technology application to be seen over there. Now, some ongoing challenges in this regard include the fact that we have a lot of electronics still connected to these devices. And since these magnetometers are picking up magnetic fields, that also includes the magnetic fields generated by the equipment that we're using. So that means the data that we're seeing is not just from the brain, it's data from the equipment of the backpack, it's data from all the other electronic sources around us. And to some extent, it's also the magnetic fields from the Earth as well that are being picked up by these sensors. So that's an ongoing challenge. And the way we solve it is that we put the participants in a magnetically shielded room. So it's a big room, it's like a box, it's magnetically shielded, which means it's limiting the amount of magnetic fields from the environment that are coming in as much as it can, so our data looks really clean. And there's a lot more interactivity that could be improved that we're trying to work on. And there's a lot of noise suppression and noise mitigation techniques that are being explored at the moment. So these are the ongoing challenges. And in terms of the outlook, is that these sensors are becoming better and better each day. And for instance, when I mentioned noise, a lot of them are now including some built-in noise canceling capabilities, like mounted coils that can basically reproduce the same magnetic fields that are coming out from the outside, but in the opposite way. So it's similar to how noise canceling headphones are working, because noise canceling headphones, when you're getting environmental noise, they're recreating the same thing, but in the opposite direction, canceling out the net effect. And that's what we're trying to do on these newer generations of sensors as well. And then we're also trying to create stronger noise models that cancel all the noise so that we can get cleaner data. And that means maybe we can have participants dancing and moving around, and we can still distinguish the real brain signal from the rest of the other signals that are coming from maybe vibrations or movements and stuff like that. So that's the direction we're heading towards. And yeah, a lot of motivation is coming from solving or at least diagnosing some spatial impairment or neurological disorders like the Alzheimer's disease. So Alzheimer's disease is a big problem, and it's projected to only get worse over time. What these headsets are offering us is a way to put these headsets on participants that are at risk. Maybe we could do some experiments. Maybe we can learn more about how their brains are functioning, and that could potentially give us diagnostic capabilities to say, okay, this person, based on the brain's performance, they might be developing Alzheimer's in the future. So that's all I had to say for today. Thanks for listening. And at this point, I'll take any questions that people have.
Very impressive, Kian. Let's
Thanks.
start queuing up the questions, Ayelen and Karime or Tanibeth. And I would like to ask you a question. Have you looked into research in areas where the magnetic field is lower? There's a place called the South Atlantic anomaly that has a pretty low magnetic field. I'm just curious if research has been done with.
Interesting. So this is like a geographical location with low magnetic fields. Is that correct? Okay, I see.
That is correct.
Well, potentially, if we can take those OPM headsets over there and test it out, that'll be interesting. But at the moment, we really have to be getting to extremely small values of external magnetic field. So even if there's like an ambient environment that has less magnetic field from other places, the field numbers we're talking about are, 50 nanotesla, which means you really need to have like a shielded room canceling most of the things out. So that's one of the ongoing challenges, the fact that we don't have the capability to do these measurements outside in an ambient environment. Right now, it's only restricted to these magnetically shielded rooms, which means there are some countries with very interesting cohorts of neurological diseases that we would like to study, but they just don't have the infrastructure for us to take these headsets and do those experiments. So we're hoping that as these sensors get better, we could be taking these measurements and experiments outdoors and in ambient environments, but not yet at the moment.
Well, that's beautiful. The fact that you're able to image what they're thinking is pretty impressive for the research where it is. Let me get to you some questions. Okay, Karime or Ayelen, looking for the live questions in Discord. Give me 1 second, Kian.
No worries. I think Juan Carlos raised his hand.
Well,
All right,
in the
Kevin would
meantime,
like to know, how do you distinguish the outside magnetic fields you're trying to cancel from the ones you're trying to measure? Do you have to use multiple sensors?
Yeah, that's a great point. So conventionally, the way it's been done with these superconducting sensors is that they've actually had something called a gradiometer, which is basically two sensors on top of each other. So the field you're measuring is actually a relative field. And that means, if it's only relative to these two sensors, it's automatically canceling or not taking into effect all the external stuff beyond these two sensors. Now, that's an ongoing problem with these new OPM headsets. And the way we model the external noise is based on spherical harmonic modeling. And it gets a bit more mathsy and technical at this point, but we're estimating the background field to be homogeneous, which means it's a very simple principle that if this is the participant's brain or head, let's say we have a sensor over here, the distance is r to the source. Now let's take this red sensor. The distance is going to be r plus h, h being almost the diameter of our head. So if the source is further away and far enough, let's say, the relative signal is going to be r squared over r plus h squared. And as the limit of r getting extremely big, which means the source being really, really far, that just cancels out being equal to 1. All this is trying to tell us is that we can treat the background magnetic field in that room as a constant value, which means when we're in that room, the background field from the entire environment is just one constant value everywhere. And all we have to do is just subtract that value from the data that we're seeing. And that should take care of it, at least to a very simple first order approach. Now, there is ongoing research to extend this onto higher and higher modes to make it more accurate. But that's just the most basic approach we can have to cancel out external noise, to treat it as a constant value or to estimate it as a constant value.
That's very impressive. Kevin, let us know if that answers your question. Next question, Kian. I'm just curious, in the experiment where 8 people imagined moving forward and backward and so on, were the same brain areas activated on all the participants? How was the sample selected, and were there any differences observed?
Yeah, great point. So I myself wasn't too involved with the actual experiment. So I'd like to make that clear and give credit to where it's due. But I will answer in the sense that the source localization process is averaged across all 8 participants. And they did see that if you average that, this is the spot that is lighting up essentially. So that result that I don't have a plot of it, but let's imagine it's the plot to the right over here. Let's imagine that was from this experiment. This is a plot that's been averaged over all 8 participants, and we see it light up. And that essentially agrees with what the neuroscientists had demonstrated with other technologies and means, like conventional MEGs or different types of experiments. So it reinforced our assumption that spatial navigation, for instance, is coming from this particular area or domain. But of course, if we had more resources, having more and more participants would only make the results more accurate. So we are limited to these 8 participants as preliminary results. But there's a lot of averaging going on between all these participants.
Makes a lot of sense. And with the, someone here is asking, Daniel in Costa Rica, if the LK99 was actually at room temperature.
LK9, is that the room temperature superconductor that came out last year, like in summer? Okay. Well, I think this was debunked. Otherwise, quantum computing would be a thing at the moment. So unfortunately, that wasn't true. But that just kind of reminds us of the need and the excitement that we have to find a room temperature superconductor, because there are a lot of applications for it. You know, we know the applications in quantum. These are very direct, and these are things that we're interested in. But also thinking bigger than quantum, all these brain imaging technologies as well could benefit from it. So sadly, that wasn't real, but a lot of ongoing research is going into finding out how we can find better superconductors or more room temperature superconductors.
Yes. All right. Thank you, Kian. Do we have any more questions? Kevin said that it answered his question, and Danielle did too. Okay.
I think Juan
Yes.
Carlos might have a question. Yeah,
Yes,
go
I
ahead.
have a question.
Oh,
Well,
Juan
thank you so
Carlos,
much, Kian. Your presentation
go ahead.
was truly amazing. And I just wanted to ask you, is there any basic requirements that candidates must have before be part of the trial? Or how did you select the participants?
Yeah, that's a good point. Again, since I wasn't too involved with the actual experiment, it's what I can answer is limited in that case. But I will mention that the requirements are healthy individuals, healthy in the sense that maybe there was no brain surgery or they haven't had any neurological diseases in the past. So that's the sampling set of these 8 participants. Other than that, it was really whoever we can find, as long as I think they satisfied that criteria. That was the main thing. So we haven't looked at things in terms of age or other factors actually. Yeah, as long as they just haven't had any of these issues in the past, that made them eligible.
Thank you so much, Kian.
Yeah, of course. I think Nydia, you might be muted.
Hi, Kian. I actually have a question for you.
Yeah, of course.
More in the medical field, so I'm curious about is there a baseline for the electromagnetic readings that the body gives off of just each participant?
In terms of the readings, I could tell you the sensitivities we're looking at are, these sensors, they can capture up to 15 femtotesla. So whatever we're reading is actually below 15 femtotesla. And I think in that case, it depends on the exact response that we're looking for. Some responses are a lot bigger, some a lot less. But a key metric, I would say, again, everything has to be below that, roughly along those numbers, 15 femtoteslas, or in that scale effectively. But apart from the value of the magnetic field, I think another metric of interest is actually the frequency of these signals that we're seeing, of these magnetic field signals. So if I have a plot of the frequency quickly, that might be.
So the reason I'm asking is since, I think we have a lot of interaction within our bodies of frequency and just kind of the energy that we're giving off. If it would be interesting to see if you were able to have two participants in the room and see if you were able to communicate through ways like just thinking of each other, and to see the readings between the impact of just the electromagnetic sensors, see how that
Absolutely. Yeah, absolutely. And I think as these sensors get better, again, it's going to allow us to do a lot more complicated experiments. Right now, even the fact that it's pretty amazing that we can get these readings in terms of navigation, it's still very elementary and kind of easy to capture, and they've been captured from other technologies as well. But as they get better, as these things get more sensitive, then we can be understanding a lot more deeper things that go on in the brain. Perhaps with what you're mentioning in terms of like interactions between two participants now, and how that's leading to changes.
So potentially you could prove that telepathy is a real thing.
We'll see. Give us a couple more years, I think. We might need a bit longer than that. But yeah, I think that these are the questions that would be interesting overall, and we're hoping to get to at some point in the future.
Thank you so much for your presentation. It's an honor.
Yeah, of course. Thank you for having me again. And at this point, maybe I'll stop sharing, and that's okay.
That's wonderful. Thank you. That was Dr. Assaf. She's quite curious about how quantum can be merged with our medical field, and we do have a line that is talking about quantum for good and quantum for in the medical field. So if you are interested in this, please reach out in the Discord channel. We have several interns that have been doing research, and individuals that are looking deeply into what it looks like to have this sort of thing. So Kian, we're getting a lot of positive feedback in the chat also. So thank you very much for your time and dedication. We know it's quite the time for you, so you can stay and join us. We thank you for being up at this time, or you can go back to sleep. So thank you very much.
No worries. Thank you very much again for having me, and it's great that you're doing this program. I think that's amazing, and best of luck and good luck to all the students.
Thank you so much.
Take care.
All right, so while we prepare for our next speaker, we're going to just do something a little silly, I guess. And it's going to be more or less walking you through what I would like to say are quantum gates and a visual exploration while we get Alejandro ready for his presentation. And so in the IBM challenges that we're going to be going through this week, what we're going to do is we're going to give you a basic level and intermediate level. At a basic level, one of the badges directly from IBM that you could earn is based on information. Now, at this point, we are getting it to We've talked about single systems, some of the aspects of multi-systems very basically with other metaphors. So what we're going to do right now is look at just some of the quantum gates. Now, in the quantum world, we understand that instead of, bytes, we have qubits. And when we sent the videos about the Block sphere, it was to help some of those of you that are a little bit more visual to imagine these vectors through a Block sphere, and the position that they were in would be the measurement of what their, where they are measured at that point in time. If you consider that we do not make measurements in a quantum way, you would have to, we have to measure things classically. We don't have really quantum. And that said, when we create circuits, we're going to initialize in our Qiskit code, right? We're going to create a quantum circuit and a classical circuit. And as we move along, you're going to see that there are certain algorithms or operations that might require auxiliary qubits. So today we're just going to talk about the basics, some of the main gates. In the recordings, you also had access to the Hadamard gate recording, and that is one of the key operations and key gates. What happens, it's explained in so many ways with the double slit experiment, with the tossing of the coin. First time we just kind of went through a PowerPoint very briefly of what that looked like, but pretty much you have a 50-50 probability of heads or tails. And when we look at the Hadamard gate, how it creates, it creates that state that we want those qubits in, you'll start noticing trends. And a part of the trends that we want to walk you through have to do with whether you need to initialize qubits in order to be able to apply a NOT or an X gate, whether you need to apply a Hadamard gate, whether they're now in superposition, are they entangled? How are you getting to these states so you can create the operations that you need? In our quiz, which, by the way, congratulations, everyone. We have an incredibly high pass rate, and we're not surprised because we have a lot of brilliant people. We want to make sure that you get the opportunity to truly learn. So take advantage of the people that are ready and able to help you. We have several one-on-one classes, and we had some of the office hours did have multiple participants, but I encourage you to take advantage of the fact that we have so many people that are readily available to support you, to answer your questions, to go through the material. Dr. Bergman answered several questions, was happy to do so, and so did Sudikin and myself and Ayelen and Sebastian for some of the Spanish speakers. So please don't be shy. Very well. I'm going to share my screen while we prepare for Alejandro, and we're just going to go through some of these basic gates. But we're going to do it from a visual exploration. In this world, we have the X gate, the Z gate, and the Hadamard gate. I'm not going to go deeply into the Hadamard gate because you already had a recording there, and Javier, who was the intern that created this. He is from Costa Rica, and he studies at the Tecnológico de Costa Rica. I'm not sure that he's on here, but if you are, let us know in the chat so you can turn your video on and we can share some of your work. That being said, all of this is just analogies. So when you think about an X gate, think about a qubit mood light switch that takes you from a smiling state to a frowning state, a 0 state to a 1 state, and vice versa. Remember that operations, depending on the order, and may be reversible. This one is known to be reversible. Reversibility is quite the topic, so just don't think it's global. If you think about this being interchangeable, right? You could go back from happy to sad. This is the code, qc.x.qubit. And so the qubit number, what this ends up being would be the position of the qubit in your quantum circuit. So it's going to be maybe 0, maybe 1, maybe 2, maybe 3, and it's going to go based on the size of your quantum circuit. Like I said before, we're going to have a quantum register and a classical register in order to be able to observe the state that observe or measure the quantum circuit. We're going to then put that into the classical register, and that is what we're going to read out. And this is going to be part of your challenge for this week. When you think about a Z-gate, think about the attitude phase. So it switches between a positive and a negative phase. And in this case, when we are in a negative phase, this is additional information. So in your mind, think about it as a shadow that can be read, that can also be measured. The cup remains, right? When we measure the probabilities in your shots, you're not, I put intentionally shot glasses here because I want you to think about measuring these circuits as shots. You're going because that's how we define it in Qiskit circuit. So you're going to be measuring it 100 shots, 1,000, 10,000, and it's going to give you how many times it was 1, how many times it was 0. You're going to start observing different trends there with your simulator. So just keep that in the back of your mind that the shadow is part of the phase, and this becomes critical for next step algorithms like phase, dynamics like phase kickback, Grover's algorithm, Hamiltonians, etc. So the negative phase, understanding how to get there either through the Z-gate or Hadamard is very important. Okay, let's go. We'll come back to the assignments here, and if Alejandro is ready for us, we can move to his presentation, or we can go into the Hadamard presentation briefly. So I'll just ask Alejandro.
Hola.
Hola Alejandro, ¿estarías dispuesto a presentar un poco más temprano o?
Sí, por supuesto, claro que sí. Si me permites, comparto
Perfecto.
pantalla.
Entonces, sí, adelante, thank you. Espérate un momento, voy a compartir pantalla para presentarte y
Claro.
we're going to do a switch of our languages. So let me stop the live translation here and see if I can make someone else. Well, first I'm going to introduce you to everyone. Please go into the translation feature. And if you speak English or you speak Spanish or you want closed captionings in a different language, select it because we're about to get, we're going to switch streams. So let's see how this goes. First, I'm going to introduce Alejandro, and then we're going to attempt this this live switching of the languages. So Alejandro, I am very, very excited to have him in our session today. We were planning this, Ayelen introduced us, and it was a great conversation about opportunity based on knowledge. And I think that everyone here has the chance to learn something that is ahead of the hype. Not only can you start thinking about it and opportunities for yourself within your work environment, but also the opportunities that you want to create for yourself long term. And if you have an entrepreneurial mindset that is that is someone having trepidations, the intent is to help you understand what the experience is from taking some, knowledge to business and what that looks like. So he's a founder actually of QNow, and he's bringing a robust technical background in data science and chemistry. He has extensive experience in the pharmaceutical and software industries, as well in research laboratories where he specializes in data architecture and strategy. He's passionate about bridging the gap between critical thinking and decision-making. Alejandro is dedicated to leveraging science and technology to drive innovation. So thank you, Alejandro. I'm gonna go ahead and share your screen, and I'm going to make, Danny Beth, I'm gonna make you the host, okay? And then I am going to attempt to do the English translations. So while Alejandro shares his screen.
¿Me confirman? ¿Están viendo pantalla?
Yes.
Sí.
A ver. Sí, espérate un momento, no empiezas todavía. Déjame cambiar esto. I can find. Actually, Johan Carvajal, can I make you host? Or let me find Danny Beth. Sorry, folks. We have. Oh, okay. So, Shireen, would you be okay? This doesn't seem to be working the way that we had planned it. So, would you be willing to switch from English to Spanish? See if I can end this. Okay. To all the Spanish speakers, we're going to try it this way. To all the English speakers, we're going to switch into interpretation. Please make sure that you have your language selected on the 3 dots in the bottom, so you get the right channel. And Alejandro, empecemos.
Muchas gracias y gracias por la paciencia también. Bueno, el propósito de la charla justamente tiene un objetivo y es de alguna manera empezar a moldear el mindset que tenemos cuando estamos hablando de hacer computación cuántica y buscar hacer negocio de la computación cuántica. Entonces, por eso es el nombre del conocimiento en quantum computing a oportunidad de negocio, hablando concretamente de cómo, entendiendo la computabilidad, ¿cierto?, de las cosas, podemos llegar a hablar de oportunidades de negocio realmente en un contexto concreto. Entonces, más o menos la agenda va así. Primero, hablar sobre la importancia de entender el problema. Sí, es tan natural perderse cuando estás haciendo un emprendimiento de una empresa de autos, que es importante mapear el problema, y todas las empresas que emprendemos contamos con ese mismo inconveniente. Entonces, en el contexto de la computación cuántica, vamos a hacer una pequeña conversación sobre lo computable, lo difícil de computar y una mención sobre las cosas incomputables. También vamos a hablar de Quantum as a Business Opportunity y hablar de alguna manera estas expectativas realistas que hablan del hardware que tenemos actual, cómo nos limita de alguna manera, y también tener un espacio para hablar de los startups, de las compañías, de las inversiones y en última instancia de la carrera que tiene que ver con la computación cuántica. Bueno, y por último, un apartado sobre lo impensado. Ahora, cuando hablamos de entender el problema, traigo a colación una frase que es un libro realmente de un señor que se llama Uri Levine. Él es el creador de Waze. Es un emprendedor serial, si se puede y si se me admite la expresión, porque se conoce al señor como un emprendedor bastante avesado. Él básicamente propone que es más importante enamorarse del problema que de la solución. Y con esto, y traigo aquí un problema matemático bastante famoso en computación cuántica, y es porque si estás buscando hacer negocio en quantum computing, lo primero que te vas a encontrar es un muro y te vas a preguntar, bueno, ¿y dónde lo aplico? Ahorita estábamos viendo un ejemplo magistral de cómo el conocimiento no, mucho de computación cuántica y del hardware físico y de sensores y de un contexto muy concreto, cómo podían apalancarse, ¿sí? Pero para quienes están empezando en el mundo de computación cuántica, se van a encontrar con un puño, de alguna manera, en el que no hay forma de machear esos problemas concretos con casos de la vida real y pareciera borroso, pero no todo está perdido, pues, porque hay una presencia lógica y es lo computable. Lo computable, cuando hablamos de las cosas que son computables, se habla de que se pueden resolver en un tiempo concreto, ¿cierto? Usando pues como algoritmos conocidos. La mayor cantidad de algoritmos que tenemos, por ejemplo, para ordenar una lista, un quicksort, ¿cierto? Un ordenamiento, una base de datos, son operaciones que ya tenemos conocidas de alguna manera, y hay otras operaciones que modelamos sistemas físicos de la mecánica clásica. Eso está muy bien, ¿sí? De alguna manera está bien, pero tiene un límite, porque no todos los problemas caen en el mismo conjunto de problemas. Entonces, dentro de una conversación muy ligera, de alguna manera podríamos clasificarlos como fáciles de computar, medianos de computar, por ejemplo, encontrar el camino más corto en un grafo o en una ruta, ¿sí? Hasta problemas que son difíciles de computar, pero computables, como factorizar números enteros largos, ¿sí? Y resolver problemas de satisfacibilidad, como los problemas de SAT. Bueno, entonces, ¿qué pasa? Que como han visto, la computación cuántica es acerca de problemas difíciles, ¿sí? ¿Qué quiero expresar? Que la computación cuántica debería pensarse tradicionalmente en el software o en la ingeniería de software, debería pensarse es como un coprocesador. ¿Cómo así? No va a llegar a reemplazar la computación cuántica, la clásica. Es una discusión que se puede tener, es verdad, pero no precisa, porque en algún momento lo podemos ver como procesos que vamos a poder ejecutar en estos computadores especializados que de alguna manera van a facilitar que demos solución a problemas de un mundo real. Ejemplo, cosas de difícil de computar que tienen nombres y nombres que no aportan mucho a dónde los aplico, pero que ya vamos a conversar un poco sobre eso. Ejemplo, el problema de los grafos isomorfos, ¿sí? O el problema de encontrar los maximum click o subcomunidades en un grafo, o el problema de cómo yo particiono un grafo de manera óptima, ¿cierto? Hay un conjunto de problemas que así, a simple vista, no tienen ningún sentido interesante, pero lo que yo quiero traer a colación es justamente porque hay una especie de característica en la dificultad de computar este tipo de problemas que es atractivo llevarlos al computador cuántico. Y muchas de las soluciones que estamos viendo que vamos a ver en el futuro tienen una raíz en este concepto. Entonces, para muestra un botón, hablar de, por ejemplo, diseño de materiales y optimización de procesos, ¿sí? Hablar, por ejemplo, de justamente yo como modelo las propiedades de un elemento, ¿cierto? De un material, es muy interesante. Ahorita estábamos hablando hace un instante sobre cómo yo voy a utilizar la computación cuántica en el mundo de healthcare, por ejemplo, para disminuir el tiempo en que encuentro un medicamento. Eso es muy interesante. Tiene sus retos, ¿cierto? Pero es justamente esos retos lo que hace que nosotros estemos constantemente buscando soluciones para optimizar, mejorar como un proceso o dar una solución. Pero todo está alrededor de una necesidad, de un problema. Ahora, para hablar un poquito más de lo que es difícil de computar, existen de alguna manera paradigmas en la computación cuántica actual, como la tenemos. Entonces, para explicar más o menos como esta matriz, veámoslo así. Tenemos computadores clásicos, una columna. Tenemos el principio del quantum annealer, que por ahí el proveedor, el más famoso es D-Wave, y se van a encontrar que trabaja bajo un principio diferente. simuladores cuánticos y se van a encontrar computadores cuánticos que están basados en compuertas, ¿cierto? En este caso, IBM, la propuesta de IBM es esta de por acá. Y justamente se habla sobre estas dos eras. Actualmente nosotros estamos ubicados acá, ¿sí? Esta es la era ideal donde básicamente todo pues, puede funcionar muy bien en una teoría pues, que la soporta, donde hablamos de una ventaja. Pero si podemos hacer el match de algunas de las cosas en este momento, son muy pocos los casos prácticos que tenemos porque nos falta investigar más en las tecnologías que facilitan esos avances, ¿sí? Entonces, de alguna manera, en el tiempo, o sea, esto es una carrera en el tiempo, me parece muy interesante, es porque lo que no sembremos hoy no lo vamos a poder recoger mañana, ¿sí? Entonces, si decides estudiar, por ejemplo, sobre variational quantum eigensolvers para resolver, por ejemplo, el ground state de una molécula chiquita y funciona y tienes una ruta que te va bien, está bueno que hagas una investigación por ahí y veas todas las limitantes que tienes con ese tipo de solución que quieres brindar a ese problema concreto. Es decir, problemas hay. ¿En qué sentido? Hay problemas de búsqueda, de optimización, de quantum machine learning, que es muy interesante en este momento. Hay problemas de simulaciones físicas. En química inorgánica se van a encontrar muchos problemas. Eso es un problema clásico en criptografía y criptoanálisis, que es pues, integrar en números enteros. Y también hay un campo muy interesante que es el Quantum Inspired Algorithms, porque básicamente es tomar de inspiración justamente los principios del reino cuántico para crear algoritmos nuevos. Entonces, con este diagrama lo que busco es de alguna manera segmentar esa especie como de visión. En el primer slide de arriba, en la primera parte, la idea es observar que hay algunos problemas que hacen parte de las cosas que ya conocemos en el flujo de ciencia de datos, por ejemplo, tradicional, un clúster en una clasificación, tareas del deep learning y muchas otras que de alguna manera tenemos soluciones o aproximaciones que las podemos hacer clásicas, pero que también podemos traducirlas a el reino o la capa de algoritmos cuánticos, que a su vez allá afuera hay muchas herramientas que buscan resolverlas en su forma, ¿cierto? Cada uno tiene su propia propuesta y cada, de alguna manera, problema tiene su don de computarse, ¿sí? Es más eficiente computar de alguna manera, o es más correcto computar de alguna manera en un anhiller un problema de optimización, ¿sí? Voy a poner un ejemplo. Entonces, sobre lo difícil de computar, el mensaje aquí como para captar lo más importante, yo creo que es esta diapositiva, en el sentido de que en el contexto de computación cuántica, lo que más nos va a interesar es ver este tipo de problemas que todavía estamos explorando en la vida, y es el BQP, ¿sí? Básicamente estás probando, o es un tipo de complejidad de problemas que describen que los problemas pueden ser resueltos en un tiempo polinomial, pero con un error asociado probabilístico. Ahora, un ejemplo de esos es el famoso algoritmo de Shor o el UAUA, ¿sí? Listo. Ahora, hasta ahí la parte gruesa, la parte donde nos interesa. Quedarnos en una parte de algoritmos BQP que resuelven problemas NP, por ejemplo, ¿sí? Y que pueden ser interesantes de resolver con un computador cuántico. Ahora, nuevamente, enamorarse del problema y no de la solución. ¿Qué quiero expresar? Hablemoslo en términos de problemas para cambiar o dónde poner el mindset. Estos problemas son clásicos de ciencias de la computación. En un curso de ingeniería los vas a ver, te los vas a encontrar. Es el problema, por ejemplo, del bolsito donde vos estás buscando distribuir o en el morral, ¿cierto? Que vas a ir al monte, la mayor cantidad de recursos que sean valiosos. Entonces te vas a dar cuenta que no hay de alguna manera una solución óptima, vea que van creciendo la cantidad de cosas que tienes que guardar en el morral, ¿sí? Y el TSP es el famoso problema del viajero. Necesitas encontrar una ruta, ¿cierto? En tu negocio para que tus vendedores vayan de una manera óptima del A a B, luego de B a C, etcétera, y que regresen otra vez pues a la empresa, ¿no? ese tipo de operaciones que parecen triviales y no son necesarias, son muy importantes, por ejemplo, en logística, porque estás buscando de alguna manera generar lo que es muy buena distribución de los recursos, por ejemplo, a menor costo. Entonces, de alguna manera, exactamente se evidencia que hay problemas que necesitan una representación matemática que nuestros computadores clásicos no se resisten a dar buenas soluciones, y que un computador cuántico, por estar en ese dominio de problemas o ese dominio de cosas que puede solucionar, se ve muy bien haciéndolo. Uno de esos problemas es el problema del max cut. Se han explorado un poco los Jupiters de IBM en estos últimos días. Ha salido un programa muy interesante de resolver con el max cut. Está bueno el Jupyter, por si lo pueden chequear en los elementos que ellos tienen. Y otro problema muy interesante que también está asociado con grafos es el critical path, justamente cómo es que yo necesito asignar unas tareas y unos recursos, cuáles son las tareas más críticas para que pues, la tarea se cumpla, ¿sí? Entonces, la idea o la invitación es llevar de esos problemas que las empresas tienen en todo momento, cuáles son los problemas que son difíciles de trabajar o que se resisten a computarse, ¿sí? Entonces, vamos a hablar un poquito de las expectativas realistas, dónde poner el mindset nuevamente. Entonces, este mensaje es para que cada vez que nos encontremos con una información, incluyendo esta, incluyendo toda la que se encuentran allá afuera, primero leer, actuar después y de alguna manera cuestionarse siempre. ¿Por qué? Porque en el hype de la tecnología muchas veces hay desinformación, y es parte de nosotros que estamos estudiando, que nos gusta la disciplina, valer por un mensaje transparente, ¿sí? Bueno, lo otro sería echarle un ojito justamente a este tipo de complejidad algorítmica. ¿Por qué? Porque no todo el mundo se dedica a hacer algoritmos nuevos, ¿cierto? En las disciplinas, como en todas las disciplinas, hay especialidades. Puede que tú seas un developer que está implementando quantum computing en una API para hacer un job de, no sé, una ruta de suministro óptima, no sé, y no estás diseñando un algoritmo nuevo, pero cuando te enteres que estas implementaciones ya están disponibles en X o Y computador, para ti va a ser más fácil acceder a ese servicio, ¿sí? Lo mismo que si eres un entrepreneur o una persona que simplemente quiere experimentar. Esto es buena idea a nivel técnico, echarle un ojito. Lo otro es aterrizar un poco las cosas y recordar siempre que estamos en la era ruidosa, de alguna manera. Así que todas las cosas que nosotros hagamos en la era ruidosa tienen que considerar justamente las técnicas de mitigación, de errores que seguramente se van a encontrar a lo largo de los cursos que vean. Siempre es importante tener en cuenta que si van a hacer negocio, les van a preguntar que si pueden hacer teleportación y cosas que las personas que están afuera del contexto preguntan, siempre es bueno hacer un llamado a la calma para bajar la expectativa sin perder el interés. Y aquí voy con esto. No permitir que el miedo a quedarnos afuera nos nuble el juicio, ¿sí? A nivel técnico es muy bueno seguirse exigiendo, y más con tecnologías emergentes. Lo mismo cuando querés hacer una inversión de un nuevo negocio, pero no significa que sea que vayas a invertir todo tu negocio en, no sé, explorar qubits, ¿sí? Sin contexto previo, sin investigación previa. No, es leer primero, actuar luego y preguntar siempre. Y lo último, que es el mejor consejo que puedo como compartir, es identificar los problemas intractables de las compañías en las que estén trabajando. O si quieren montar una empresa, identificar cómo el problema que es intractable, ¿cierto? O difícil de computar, se relaciona con tu necesidad de negocio. Esa sería la salsita secreta. ¿Por qué? Porque vas a necesitar tener un portafolio de necesidades que puedas matchear con, esto es supeditado a resolverse con computación cuántica. Si no, no vale la pena. Porque no es un nuevo super servidor como los clásicos. Es un coprocesador que puede ayudar a los clásicos a resolver problemas que ellos no pueden, ¿sí? Bueno, en esencia, para ir finalizando la charla, existe un ecosistema importante de startups en Estados Unidos, ¿cierto? No hace falta mencionar que por acá está IBM, hay en la Universidad de Duke, en DARPA, hay compañías Microsoft, todos ya conocen un poco de eso. En Canadá también la gente está más asociada con Xanadu, con D-Wave, en el término de cómputo, ¿cierto? ¿Por qué? Porque el término de software, de gente que hace software y, por ejemplo, trabaja con Quantum Sensing, no se escucha mucho, porque siempre escuchamos es computación cuántica. Recordemos que hay otras vertientes de hardware y cosas interesantes por mantener a la vista. En Europa está Orca Computing, Oxford, Riverlane, y en Sudamérica están estos pequeños grupos de computación cuántica. Los traigo a colación, parte porque pertenecemos a un grupo de estos y parte porque no hay en la región un mapa concreto que muestre a la TAM como un nicho donde hay muchas inversiones. De hecho, eso es lo que vamos a ver a continuación. El mapa de inversiones justamente en Latinoamérica, que es donde resido en este momento, es muy bajito, lo mismo que las regiones en el África, Medio Oriente tampoco. Hay mucha inversión. Las inversiones normalmente se concentran en Estados Unidos, Canadá, China y demás países. ¿Por qué el llamado a la acción? Es porque es un océano azul en potencia. Es decir, donde no está este mercado, existen oportunidades de educar para que exista ese mercado. ¿Sí? Que es lo interesante. Y ¿qué acontece con esto anterior? Que te vas a encontrar que cuando se busquen implementar justamente inversiones y proyectos de computación cuántica, todos los que te encuentres están supeditados a una carrera en computación cuántica. ¿Sí? En esencia, a cómo yo voy a establecer este sistema que sea de alguna manera universal, que facilite el cómputo y que facilite muchos problemas o la resolución de muchos problemas. En la práctica, eso no es tan así. En la práctica, lo que vemos es que hay unos que funcionan mejor para ciertos problemas y otros para otros, unos que escalan muy bien, unos que escalan torpe. Entonces, los invito a que, si bien estamos participando de un evento, mañana de otro, siempre leamos, actuemos y preguntemos siempre. Y en última instancia, el mensaje es sobre lo impensable. Me gustaría pensar que el día de mañana la TAM se pueda convertir, ¿por qué no?, en una potencia de talento de gente de Quantum, de personas que saben de Quantum Software, que trabajan en la TAM, para la TAM y de la TAM hacia el mundo. No que tengan que irse de la TAM a trabajar en el mundo. Y nada que venga pues verdaderamente valioso es fácil de hacer. Y nada, muchas gracias.
Muy bien dicho, Alejandro. Muchas gracias. To everyone that was in the English channel, I am very sorry. We had some technical difficulties. We will translate the session and make sure that it gets to you. In that being said, please make sure that you have your closed captioning with the real life translation in the closed captioning, and that you have selected to see the transcript so you could see everything translated in real time, as we've said several times during the presentation. Very ambitious of us to do things in 2 languages, but all we could do is try our best. So Alejandro really walked us through a very motivational, very in-depth approach of where the opportunities are and where they are not yet. And I think that as there's a lot of hype, we tend to not have, there's so much misinformation that when you're actually looking at applications that can be monetized right now, you need to know what is real and what is a different what is aspirational currently in research. That being said, I invite you to ask questions for Alejandro. Voy a ver el Discord. Acá un toquecito. Pero without getting into issues of immigration. What he's saying is that it's good to create opportunities where you are. That so especially in Latin America is a very big market, and for those of you that are in different countries, it would be great for you to create your opportunities there. All right, so Jimmy is asking, what does Q Now do? What is the purpose? What is the problem that you are loving? Alejandro, go ahead.
Claro que sí. Bueno, en QNow hacemos lo que es minería, extracción y generación de conocimiento. Extraemos de alguna manera grafos de conocimiento de data no estructurada de nuestros clientes para hacer automatización inteligente. Bueno, ¿y eso para qué? El propósito es automatizar esas tareas que son dolorosas, ¿sí? Como de alguna manera la revisión de un documento, la extracción de entidades de ese documento, la interpretación de un contrato, el cálculo de un profit and loss y de alguna manera incluso la revisión literaria. En investigación acontece que la revisión literaria es un proceso muy extenuante, ¿sí? Con nuestra infraestructura puedes de alguna manera automatizar ese tipo de acciones para sacar la mayor cantidad de valor. Y bueno, ¿cuál es el problema que nosotros amamos? Justamente ese, que el problema es que el conocimiento se muere con nosotros y no lo podemos transmitir a nuestros hijos. No se hereda. Yo cuánto quisiera que mi hijo supiera lo que yo sé, pero eso no pasa. En la realidad, esos conocimientos dejan de traducirse a cosas útiles porque no pueden heredarse. Si encontramos una forma de heredar ese contenido semántico que nosotros tenemos como humanos, pues nuestros sistemas del futuro van a ser muy inteligentes y pues idealmente tomar mejores decisiones de riesgo, mejores decisiones de negocio sin tanto riesgo, en esencia, pues.
Me encanta. Acá tenemos otras preguntas para vos. Ah, bueno, a ver, parece, dice que Guille Casa, gracias muchas gracias Alejandro por la presentación. En QNow ya tienen soluciones en producción y problemáticas de empresas reales usando cuántica. Y ahora dice, justo desde esta respuesta entendí más lo que hacen.
Claro. Sí, te podemos hablar de algunas cosas que el día de mañana vamos a conversar un poco más al respecto de la compañía y sí, efectivamente tenemos soluciones que están orientadas en este caso a cómo computar de manera segura, ¿sí? Y pues todas las operaciones que a nivel de quantum implican. Y pues el día de mañana podemos conversar un poquito más. ¿Les parece?
Perfecto. Muchas gracias. Si hay, a ver si hay otras preguntas. Parece que por ahora no hay otras preguntas, chicas. Okay, let me see. Is there another one? Okay, perfect. Bueno, entonces muchas gracias, Alejandro. QNow, vamos a tener varios speakers de QNow, tanto en los eventos presenciales de Argentina. QNow is one of our partners, and we're going to have several of their speakers. Just similar to what Kian spoke about today with quantum in the medical field. We're going to have another one of their founders speak later in the series. That being said, thank you so much, Alejandro, for sharing your perspective, and also for walking us through some of the opportunities. Aquí hay un comentario más. Alejandro, muchas gracias por tu presentación. ¿Crees que en la computación clásica, en su tiempo, la computación cuántica llega a tener una revolución tecnológica, o un antes y un después y en un futuro?
Claro, qué pregunta tan buena. Claro, a ver, siempre, cada tecnología trae una disrupción. Siempre te lo vas a esperar. Pasó con la inteligencia artificial, pero también hay que pensar que hay inviernos en esto y estos inviernos muchas veces disminuyen la expectativa. Pero sí, va a haber cambios, ya hay cambios. Los cambios más concretos que puedes ver es en quantum sensing, quantum, o sea, el diseño de quantum materials. Claro que van a haber muchos cambios a nivel tecnológico, entonces sí es disruptivo en todas las áreas que te imagines. Y nada, gracias, Nydia, a vos por el espacio, a IBM
Gracias
por
a
la
ti, gracias a
organización.
ustedes. Sí, claro, no, muchas gracias. Can you share QNow's website in the chat, please?
For sure.
O en Discord, lo que te quede más fácil. All right. Well, con eso, we're going to shift, and thank you for the patience for those of you who did not get the real life translation into English. So we will again make the recording available for you, so you are able to get the same information and valuable experience and the context of the opportunities that are out there with solvable problems. What I'm going to do is I'm going to walk us through some of the opportunities that we have in terms of official IBM badges. We, as you know, the way that we are structured is that we have these sessions, we kind of walk through certain information, and then the videos that you receive have in-depth information for you to be able to watch short snippets of information. For example, you're going to receive something on Bell states. We're going to talk about quantum gates, and you can choose the level of math that you go into. But the videos that are going to be on the YouTube channel, which I will share with you probably tonight in the Discord channel, are going to give you an approach that is developed by our interns. And we're going to have the notebooks that are going to help you test that. And in those notebooks, you'll have access to the official IBM information that walks you through the gates. Now, if you have been a quantum enthusiast for a while, you may have approached, and we have like a kind of a 50-50 mix, which is why this time I'm making things more available for intermediate learners as well. In some places, they teach it from a perspective of math into the computing gate, so you understand the operations and what you're doing at that level, more of like an assembler approach. In other approaches, if you understand how these operations work, what the algorithms are doing, you're better able to apply them to real world problems. And for example, if you find something in nature that needs a local minimum, then you can start thinking about which algorithms would help you find that within, and what type of problem would it be appropriate? What type of equations do you need? That being said, you're going to have access to all three levels of information, and we're going to walk you through some of the opportunities right now that you have for the IBM badges. Just now, remember, we are on the Discord channel with our open office hours to help answer any questions that you may have in terms of the information. So this here, you can see my screen. I should probably see my browser. This will take you through the basics of quantum information. So here, this is an example of the explanation you're going to see in the single systems is a lot more, it's a little bit more mathematical. For those of you that may not have a more recent experience with linear algebra and matrices, it might just take a little bit of getting used to, but it walks you through what we did last week with the Dirac notation, but in a more mathematical way, rather than with cats and potatoes and different evolutions of metaphors, right? You'll see here the representation of the row vectors, and as you go through this, you can either do the PPT or you could do the recording, but you'll be able to see, and I'm sorry for the scrolling here. They even talk about the stochastic matrices that Dr. Bergman went through. I'm trying to get to one point. This is important when you're talking about the transpose of the different operations, because when we talk about reversibility, which is what we were mentioning before, you will want to know that the identity matrix is something that we sometimes play around with the conjugate transpose. And so that should be, they should both equal 1. And if you switch the places, it should also be that way. But that being said, what we talked about earlier, just briefly about measuring the quantum states, in the libraries that you're going to be pulling into your notebooks, you'll see that you have the AR simulator that is part of the libraries that you're pulling. So that's what's going to allow us to measure the quantum circuit, and you'll need your classical circuit, right, to be able to measure it. And depending on how you use it, you might use shots, you might just measure and then plot with the Python libraries that we will be sharing with you in depth on Sunday. In here, let me just take you back here so we don't go down that. Single systems is one that you can do. When you get through the entire basics of quantum information, you can earn that badge directly from IBM. You're going to be receiving certificates here, and weekly based on the passing grades of your assignments. That being said, if you are and then next week we'll see multiple systems and so on and so forth. So the basics of quantum information is a badge that is achievable for you if you are at a point where it is something that you can dedicate additional time to. The recording is 1 hour, a little over an hour for each one. So that's just so you have a perspective of time investment if you wanted to do both approaches. For the intermediate level, we're going to have variational algorithms. We're going to do quantum error correction, optimization, variational algorithms. And one of the notebooks is focused on transpilers. So when we talk about this notebook over here, you'll see that it is using polyoperators, the VQE algorithm, and the ISA circuit. So we're going to do a code with me exercise on this next week for the challenge number 2, and then we're going to start a timer, and then you can deliver that. Or the third challenge based on where your level of competency or experiences with quantum. So I'll stop sharing for a moment and open it for questions. I'm going to allow folks to unmute and let us know. Just give us some feedback in terms of the recordings, if they were accessible to you. Does it make sense? Do you have questions on how you can access these things? Again, I will be sending the presentation through Discord and in the channels that we have, but I just want to make sure that if you have questions, you can. Lucas is asking, where can I find that document? I will be sharing it in Discord after the meeting. Everything that I have shared with you, I will share after the meeting. But I just wanted to kind of walk you through the levels of information and the approaches that you have in order to be able to pass these challenges. Any other questions? Let me just check Discord. Okay. No questions at the time. Okay. Very well. Oh, okay. We can proceed with the next topic. I'm just going to give this person a moment to ask their question. All right, so while they ask their questions, I'm going to talk to you about the humanitarian challenge that we have coming up. So we're going to have some prizes that are either going to be quantum hardware credits, developer licenses, and we have a surprise at the end, but what is the humanitarian challenge? I'm just going to introduce it. We would really like you to be inspired to look in the world around you and find those problems that you may want to solve, and just start thinking about the dynamics of how they occur, whether they're a logistic issue. Are you trying to optimize something? Are you trying to refine a situation that just needs to be improved because it might be cyclical? What kind of dynamic does this problem have? We're going to have a competition, and we're going to be releasing it. It will be timed, but the GitHub is being set up right now. So what we'll do is, we don't expect you to code, but we do expect somewhat of a proposal of how you would solve a situation around you. So if, for example, you think about in Latin America, many times there's some issues with logistics, or bus is arriving late depending on certain timings, and there are dynamics in logistics that could bring cost savings. And so what he was talking about, the traveling salesman solution, that is something that you could use to apply also. But we're looking for creativity in how you would solve these problems in your environment. And if you want to put in the chat, be it Discord or in the okay, no questions in Discord, or in this chat, I can read them both. But essentially, if you were to ask yourself in your surroundings what kind of problems you find, try to stay away from the politically charged topics, but we want to see, with creativity, whether you have something that could find optimizations, be it in healthcare or in other fields. Very well. Johan, any comments to that? You should be able to unmute yourself, Johan Carvajal. Okay. Very well then. So what we're going to do next, there are no questions for this humanitarian challenge, is we're going to actually wrap up early today. We had someone that could not come in, but they have a recording for us. And so rather than start a topic that I know we will not finish, we are going to send you a recording of their presentation. And if you want to just speak freely about some of the topics, I could be here for the next 20 minutes or something, and we can talk about the belt states and different things, but we can go through it a little bit more informally rather than the overall presentation. Okay. Stop the recording, and then you are free to ask your questions in a more relaxed way.